All right, well, we'll get started. Today, I decided that we'll do some data mining because that was a requested topic. And we'll start by mining some of the COVID-19 genome. So, and you'll have the Colab notebook to follow on or pad out any information that I will almost definitely skip over. Cool. Okay, so I started out on this site yesterday. It's on the NCBI website, and it contains a repository of all things COVID-19 related, including protein structures and sequences, because I'm sure you've heard that it's been sequenced a whole bunch of times all over the world. And we're going to start with this file here, which looks like this. So it's a .yaml file, which I looked into, and YAML stands for YAML ain't markup, which is a stupid recursive name, but we'll work with it. So essentially, it's a table that has each of the accession numbers and some extra information about all of the sequences that have come in over the last couple of weeks and months. So for example, this one here was sequenced in January in Shenzhen. So this is what we'll be working with. Let me fire up a new Jupyter notebook. Okay, let's call that data mining. Covered. Sure. Okay, so we're going to start with an import of a module that we've not looked at before. I think it's built into Python, so you should all have it. Import requests. This is the request library, which for more information, you can check out the requests website. So essentially, it's a library that handles making requests over HTTP, over the internet, basically, and lets us get data back, which is exactly what we want to be doing with this data mining. And this is the raw file that we want. So I'm going to copy this URL at the top here. Where are we? Okay. So if I send this command requests.get this link, it will return a requests object which has a few attributes. That's a typo. Okay, and the first thing you see is a response 200. So if you're familiar with your HTTP codes, which I totally don't expect you to be, then you might know that 200 means great success. You might recognize HTTP codes from when you get something like a 404 error when you can't load a web page, for example. I'm going to make this into a variable so I can come back to it. And we can look at some of the attributes that this variable might have, the request. Okay, so I wanna extract the text from it. So to get the text, r.text, and then we can this addresses the attribute, and I'll save that as a variable data, and we'll print that out at the bottom to have a look at that. And it is barely readable. You'll notice there's a lot of \n's in here. \n is an enter character. So these should all be on different lines. So for this next section of the tutorial, we're gonna work on making sense of all of this, because there's good information in there. We just need to structure it. Let me minimize this. Okay, so we have our object data, and we need to process it. So I did a little bit of Googling into YAML, and which is the file type that we're working with here. And there's a Python module called YAML, which helps us parse this sort of data. So I'm going to import the YAML library, which I think is also built in. Probably it's worth pointing out that prior to doing this, I didn't actually know any of this stuff. It's the sort of thing that you can find out with a fairly quick Google. YAML, and we will load the data object into a YAML object to see if it can translate it. So YAML.safe_load. Now, I learned that if you do something like YAML.load and then you load data into it, that will probably be fine for our use case, but it's good practice to use safe load because this load function will run any code in the data that you feed to it. So if there's any malware in there, then we're in trouble. So that's why we're gonna opt for the safe load. And you can see that it returns a nested dictionary. So we've got a dictionary, and under GenBank sequences, there's a list. You can see the start bracket there. And then there's another dictionary inside that, and another dictionary inside that. So I'm going to call that data YAML is equal to that. Okay, so ultimately I want to turn this into a pandas data frame, which we covered last time. Pandas, for sake of recall, is a tabular data managing library. So it can read XLs and CSVs, and it can also read these sorts of nested dictionaries, and it's bristling with useful functions to help us extract the data that we want from it. And it's my library of choice for tasks like this. On a quick Google, I found a way to pass these nested dictionaries into pandas. So this sort of dictionary within a dictionary is pretty similar to a data format called JSON, JSON, which stands for JavaScript Object Notation, I think. But essentially, that's also a dictionary of dictionaries. So we can use a pandas function designed for. Sorry. Okay, we can use a pandas function designed for working with these nested dictionaries, the JSON objects, on our YAML object. So I'm going to import pandas as PD, as a nice convenient handle. And I know that the function for reading in these sorts of dictionaries is under pandas.io.json. You'll notice I'm using a little bit of autocomplete here, which is tab. This works in Jupyter notebooks, but in a Colab notebook, to do an autocomplete, you just got to wait until it detects that you want to autocomplete. Pandas.io.json.json normalize. That's the function that I want. And I'm going to pass it this data.yaml object. Okay, so what's happened here? That looks horrible. Well, if we look back at this nested dictionary, we'll see that all of the data that we want, the accession numbers, the gene regions, and the collection dates, are stored under this dictionary value GenBank sequences. So I'm going to address the data.yaml by GenBank sequences and see what that looks like. Okay, so now this is a list of dictionaries with a little bit of nesting inside. There's a dictionary within a dictionary. But that's something that the pandas.json IO module can handle. So I'm going to pass that into the function instead. Not like that. That's horrible. There we go. Okay, so now that horrible dictionary within a dictionary within a list is now a usable, readable table. It's automatically detected the column names, which is awesome. And even the nested dictionary, which was the locality.state, has got its own separate column. You'll notice that there's a lot of NaN values here for where state wasn't specified, but rather just the country, Thailand in this case, was. Okay, so I'm going to save this variable under df for data frame, and I'll leave it printed there just in case I need to refer back to it. So what do I want to do now? Well, I want to get all of the complete genomes. So I'm going to filter this data frame by this column gene region where only the complete genome is present. So to do that, I enter data frame dot locate, and to that I'm going to pass in square brackets a Boolean function. You know, I'll take a step back actually and show you what I want to do. So to isolate this column, the gene region, I can locate it by using a dictionary style lookup within square brackets, and I want to locate only the rows where we have a complete genome. So I'm going to do a logic test on this column. df gene region equals, that's the true or false operator, as opposed to declaring that something is equal to something. Okay, so if I run this, it should return a column of trues where the genome is complete in this column, and falses where it's not. And I can use this to slice this whole data frame so that it will only return rows where this condition is met. So to do that, I'm going to wrap this this logic statement in square brackets, since square brackets is what we use to take slices and locations of the data frames, and insert in df.lock. Now, if I were to run this now, it would throw an error because this lock function expects a specification for rows, which we have here, but also for columns. Which columns do I want? I want all of them. So after the comma, I'm going to put in a colon, which signifies all of them. If I run that, so we still have a clean data frame, except only the complete genomes are in the set. You'll notice that the index here is different from the original data frame because rows 1 and 2, which were not complete, have been skipped out, and so on. I'm going to save this variable under complete. Yeah, complete should do. Okay. So what's my long-term goal now that I have a pandas data frame of all of the complete genomes of COVID-19? Well, I want to download all of them. And we can see here that that's 451 genomes. So essentially to download all of them, the important bit is the accession code. So I'll need to extract those out, but you'll notice that there's a few columns or a few cells like this one where we also have the word gapped in. that would be a problem if I try to look up this on a database, because obviously it won't recognize the gapped part. So I'm gonna isolate this column. Accessions is equal to okay. So now this variable accessions, if we print that out, should be only the accession column. Let's have a look. Okay, so I still haven't got rid of the extra words in there, so I'm going to take a operation called split, which I want to split everything before and after the column, I mean the comma, sorry, and then pick only the accession codes. Pandas string split is the function I'm after. Here we go. So here's the documentation for said function. It works on series, which is exactly what I have. Oops. And we'll remember that series is a single column of a pandas data frame. The .str is pretty much a way to access the string functions. Maybe we'll come back to that later. Anyway, accessions.str.split. And on the documentation, it takes the parameter pat, string or regular expression to split on, if not specified, split on white space. So I want to split it on the commas. So I'll feed this function a comma, and then I get something like this. It's a list for inside each cell. But easier to work with is if I specify this variable expand, which is default to false, but if it's true, then it will return a data frame with expanded dimensionality. Well, what does that mean? Let's have a look. Expand equals true. Okay, so now rather than a series, we have a data frame where each of the list items is split into its own column. Everything before the comma is in column 0, and everything after the comma is in column 1. So all of the accession codes that I want are in column 0. So .lock. Now I want all of the rows, so comma, and column 0, so 0 after. And that returns me a clean version of all of the accession codes. So I'm going to save that under a new variable called clean accession codes. Okay. So now we have all of the accession codes nice and clean, and we are ready to start mining with these. So what's the aim here? I want to loop through each one of these accession codes. Loop and download sequence for each code, and then write to a new file. Okay, so in order to write to a new file, we'll need to open a file. Open Covid-19.faster, that's what I'll call it. This is a file that doesn't exist yet, but it will when I call this function. The other argument that you need to feed the open function is either read, R for read, write, or append. There are other options as well, like read binary, but that's beyond the scope of this tutorial. I'm picking append because I'm worried that if I use the write function or the write parameter, then I will end up overwriting whatever I put in there. So I'm putting in append. Full disclosure, I'm not 100% sure if that's necessary. It's just an overcautious precaution that I'm taking. Last time, maybe it was last time, we might have covered the use of the context manager. A context manager is often seen as a with statement. With this, do something, and then it closes. Let me go into that in a little more detail. So if I were to execute this command, it would create and then open this file in append mode. I can do something within this indented block, and as soon as I'm done with the code in the indented block, then automatically the file closes. And that's useful because the file could end up being quite big. So to save memory and just to save memory really, it automatically closes. It saves me from having to type file.close. Okay, so what else can I do here? I can also specify a variable name for this file so that I can actually address it and put data into it. So with open COVID-19 faster as file, I'll call it file because that's nice and generic and I probably won't forget that. Okay, now I need to have my do something part. So I want to loop through all of these numbers in the clean accession codes. So let's create a for loop. For code in so each iteration of this loop should access one of these codes, and I want to use that to make a request to the NCBI database, download the code, write it to the file, and then close the file after I'm done with all of it. Make request. So now is probably a good time to talk about request APIs. So I've saved a okay, so this URL okay, I'll tell you what. Let me steal the URL from the tutorial document I made earlier. In my head, it's sort of cheating to refer back to the original tutorial, but okay. So what have you got here? This URL contains the address for the NCBI database. Enterez, I think, is the interface, and I'm accessing something called efetch. Everything after this question mark is the important part, though. Everything after this question mark are the parameters that I'm giving to the NCBI database to request this data. So I'm specifying database, nucleotide core database. The ampersand is used to split every argument or every parameter in this. And the last parameter I've got here is the return type. And I want that returned as a faster file, which is pretty much just plain text nucleotides with a title that is, the title is preceded by a greater than, sign or a less than sign, depending on the side of it you're standing. Okay, so this URL has got everything except the ID, where I've just left a star there. For this loop, I am going to use the replace method. Let me open a different cell. And show you exactly what I want to do here. So here's the base URL. And if I were to do url.replace, then I can specify a character to replace, which in this case is the star, which I've left as a placeholder for an ID here. And the second argument is what I want to replace it with. What have I done here? Ah, okay. If you can't see it already, the mistake I've made here is I've used a single quote on one end of the string and a double quote on the other end of the string. It's fine to use either single quotes or double quotes, but so long as you don't mix and match. So I'm going to replace this double quote with a single quote, and that should work. There we go. So you can see it's printed the same string, except the star here, as per my specification, has been replaced by XXXXX. If I want to replace it with a variable, then I can say replace it with clean accession codes number 0. Here we go. And now the ID is a valid accession code. What happens if I were to enter this URL into my browser? Well, if I paste it in the URL bar up here, it will immediately start a download. Here we go. We see that here? Let's have a little look at that. So this is the sort of output that we'd expect to get from the database. We've got all 30 or so thousand nucleotides of the virus, and you'll see that it ends in a poly A tail, which I'm sure someone who's better at cell biology than me can explain why. Stability or something like that, isn't it? Well, anyway. So let's go back to this loop. Let me move you all over here. Okay. So I want to make a request with the URL or the base URL. Let's call this base URL, where I replace the star symbol with the ID, which for every iteration in this loop will be the variable code. So making a new variable called request URL, and that's going to be equal to the base URL dot replace, and as before, I want to replace the star with the accession code, which on each iteration will be code, not base URL, code. Okay. And this request URL is what we're going to make the request to the database with. So I'm going to make a throwaway variable, r equals requests.get, and I'll paste in the request URL. So in each iteration, that should return the request items like we saw way up here. And to extract the data from it, I'll need to call the .text attribute. So let me make a variable that I'll call sequence. Sequence is equal to r.text. Okay, so for each iteration, I'll have I'll have my sequence. Now to write it to the file, which up here at the beginning of the context manager block, I've called this file. So file, and to write it, I call file.write and sequence. And with any luck, that should write the sequence straight to the file. So let's run that and see how it goes. Same problem again. I've done the mix and match of single quotes and double quotes. Okay, let's try this again. So this may take a moment to run, and I currently don't actually have a way of telling whether or not it's worked. I know that whilst I was practicing this, I kept on getting an error called error 429, which corresponds to when I'm making too many requests to the database all at once. So let me delete the file that I would have made. Okay, so I'm calling it, yeah. So in another tutorial, I think I might have mentioned that in a Jupyter notebook, if you precede a command with an exclamation mark, then it calls a Linux command. So that's what I'm doing here. Cat means pretty much print the whole file, and then I feed that the name of the file in my directory, covid19.faster. Bash doesn't require quote marks around file names. Okay, so we can see that it worked for at least one genome, maybe a couple. How about let's make this block of code more robust. So who remembers the HTTP codes that I mentioned earlier, and how if the HTTP code is 200, then that signifies that the request was a success? Well, I can put in an if statement and say if r.status code is 200, then try and extract the text and write it to the file. Otherwise, print fail, and maybe the status code as well. How about that? And for peace of mind, how about we'll have a print statement in the case that it does work. Print dot status code. Okay. What am I doing here? I am deleting the COVID-19 file that we made initially so that I can start fresh. Here we go. So that should have done that. That should have deleted that. If I use another bash command and call in ls, that should list the contents of the folder. And the COVID, this was another one I was working on before, but this file should have been called COVID-19, and you can see that now it's been deleted. Okay, let's run this now, but just so that we're not here all day, I'm going to only do clean accession codes 0 to 20, which should look like that. So I'll only loop through these 20 to save us some time. And let's go, let's write it. Ah, invalid syntax is because I forgot to add an extra bracket here. Let's try that again. Okay, so you can see it's printing out a lot of 200s, which is good. It means that we're having nothing but success. If there's a failure, then, or anything but a successful status code, then it should print that out. One of the problems I had was making the Colab notebook was that whilst I was trying to do the same thing, it would access the database so fast that I'd get a 429 error, which was a error on the database side because I'm making too many requests at once. So the way I got around that was to import this module time here. And between each request, I'd tell the Python interpreter to sleep for half a second and then do the next one. And that pretty much alleviated that problem. But that's not something that that's not an issue that I'm having in my local Jupyter notebook, so there's no need for it here. Okay, let's do another bash command and look at what's in my folder. So this Covid-19.faster file is back. Let's have a look at that. And it should have all 20 of the Covid-19 genomes that I specified for it in faster format. If I want to do something, or if I want to download the files as anything but faster, then I can replace this return type with something like GB, which is a GenBank file. And you can check the NCBI API documentation for other options. I think I've left some links in the Colab notebook that you can refer to. But if there's any information missing, then send me a message and I'll take a look. Okay, so what next? This pretty much covers most of what I wanted to do in this tutorial. I think the things that I touched on briefly at the end of my Colab notebook was how to start a multiple sequence alignment, which you would need to generate a phylogeny tree. And I found that the easiest way to do a multiple sequence alignment is to actually not use Python at all, and use a program called Muscle, which I have installed on my local machine. And to install it on a Google Colab machine, you can run, where is it? This command here, apt get install muscle. And let me break down what that does. So again, that's a bash command, because there's an exclamation mark there. That's how we know. Apt is short for aptitude, which is a software store. It's like the app store for Linux. Apt get install pretty much just says from the software, from the app store, install muscle, and that's all you need to do, and the Google machine will obey. It's sometimes common to see people write sudo before a command like this. If you see that, that just means that you're invoking admin privileges. But luckily, in a Colab notebook, you are the admin by default, so you don't need to specify that. And what I've done here is I've used the command line invoking exclamation mark to put in a command to muscle. So as a command line program, you type its name first, muscle, and then the parameters, which I found from the muscle website here, which we can have a little look at. Documentation. The website is horrible and also not secure, which is bad, but hey ho, getting started. So this is all you'd need to put into a muscle command. Let's zoom in on that. So you type muscle and then go dash in. Or a dash in most terminal commands is an option that you're supplying to the program. So muscle dash in for input, and in our case we'd give it the Covid-19.faster file, and then dash out is the name of the output. Now obviously that doesn't exist yet, but so you can call the output whatever you want. In this case, the authors have called it seeks.afa. The .file extension isn't that important. You can call it pretty much whatever you want, but for the sake of standardizing stuff and making things easier for others to read, you tend to do what other people have done. So back in this Colab notebook, we'll have a look at what I did. Muscle dash in, and in this Colab notebook, I've called the genomes file covidgenomes.faster, and I have made up a name of an out file called covidgenomes.msa.faster. This command took a couple of minutes to run on this Google machine, and I think that was only with a handful of sequences. With a 29,000 base pair genome, this could take some time, especially if you're going to do it with all of them. After I did this, I started playing around with the idea of making a tree, but then I kind of run out of time, so that's where I'm going to leave the tutorial for today. Maybe next time we'll work on plotting a tree, or there have been some requests for covering some cheminformatics type stuff, so perhaps we can look at some interesting compounds. I sort of whistled through that, and I hadn't rehearsed the tutorial, so apologies for the lack of structure. Are there any questions about anything that could be cleared up at all? Any questions?
I had a quick question about
yeah,
the error codes stuff. Is everything above 400 a bad one, basically? Is that?
Yes.
What's going on there?
So if we check out the Wikipedia page for these error codes, we get a nice guide to HTTP status codes.
I didn't see that, sorry.
So yeah, anything 400 and above, you're right, is generally a bad request. Here we go. 4xx client error, 5xx server error, and anything that starts with a 2 is generally a success. Okay. What are the other things under 200? No content, partial contents. So that's if there's a partial success. Yeah, I hope that helps. Any other questions?
Okay, so you make your Jupyter notebook available again after the session?
Yeah, of course. I will paste it onto the Slack channel.
Okay.
So one of the just as a comment, you used your with command to open a file, and then you didn't need to close the file again because the with command automatically closes it. That also means that if you have an error, it will mop up after you. So if something goes wrong and the program crashes, normally it would just leave the file open, and you can only open the file depending on what the file is. Sometimes you can only open them so many times, and you run out of files that you can open. So so that will automatically close it again at the end of that indented sequence.
Yeah,
it's like using exception handling, but I'll use. It's quite a useful tool for reminding you that you should close your files, or anything else. You're often not. It might not be files. You might be opening a network connection, or talking to a device. So it closes the connection for you.
Ah, okay. Yeah, so that's good information. Thanks, Alex. Yeah, I've only really used the with command for writing files like this, and very occasionally using certain modules. Yeah, thanks for the input. Anyone else have any questions about today? Comments, requests for next time? Issues or anything else that you'd like to bring up? Okay. Well, thank you all for coming to Python Club.
Okay.
I'll try and do another tutorial for the same time next week. And I will either learn how to make trees and show you how to make trees, or do something more in my comfort zone and do something cheminformatics C. You know, maybe read in some compounds, render them, calculate some properties, something like that.
That would be useful, yeah.
Maybe I'll do that.
Mm-hmm.
Okay. Well, thank you all for coming. And
thanks for
I'll
that.
see you all. Yeah, happy Easter, happy Good Friday, and I'll see you all in a week.
Yeah, sounds good.
Bye, everybody.
Thank you.
Cheers.
Thank you.
Thank you.
Bye. Bye.